Hi, the scope of this presentation is to exploit deep learning capabilities for energy disaggregation problem and to provide some tips in order to successfully adapt deep learning models to NILM. This research is supported by the Horizon 2020 Benefits Project. Over the last few years, deep learning has been applied to various application fields and scenarios, ranging from computer vision to natural language processing. Since then, deep learning has gradually captured NILM researchers' interest. The first reason is that in many cases, deep learning outperforms previous work, and the second reason is that deep learning can deal successfully with complex problems, such as NILM. However, applying deep learning for NILM is a challenging field because NILM is a challenging problem. We need labeled datasets to apply and to train our supervised algorithms, since each appliance has a unique different pattern signature. Appliances have various stages of operation and varying time frequencies, and among different appliances type, the signature differs. NILM is a too complex ill-posed problem, and the existence of additional noise in the aggregate signal makes the disaggregation process even more difficult to be achieved. The first proposed solution is based on LSTM neural networks. As you all know, human beings don't start their thinking from scratch. This means that every word understanding is based on previous words understanding. Also, you don't throw everything away and start thinking from scratch again. Your thoughts have persistence. LSTM networks can memorize and remember previous inputs in memory when a big set of sequential data is given to it. Household appliances followed repeated patterns of signals for a long time periods, so a short range is not adequate. For instance, a washing machine follows several operational cycles, such as pre-washing, washing, and drying, each of one related with each other in a long range. For this reason, we have used a bidirectional LSTM network. Here, we present our proposed bidirectional LSTM architecture. The aggregate signal is inserted as input in the bidirectional LSTM network. Then we train our model and check its performance. Bayesian optimization is used as a tool to tune our hyperparameters. When we have selected the optimal configuration and the optimal set of hyperparameters, then we train our model for final time, and the power load of the appliance is extracted. So, for each appliance, we have created a different BAYESIAN structure. In the diagram, you can see the performance error for 4 successive iterations for the Bayesian optimization for the closed dryer appliance of the AMPDS dataset. In the table, you can see the performance error for these iterations, and the 2 lines in the middle shows the respective hyperparameters. The figure shows the signature identification examples for the 4 selected appliances. In this figure, we illustrate the performance of our proposed method compared to that of the CNN, basic CNN form, as well as with ground truth. As observed, our approach yields better performance in estimating not only on-off states, but also more complicated energy patterns. This is important since it offers insight on whether a device is active, as well as how it contributes to the total amount of energy. Table shows the performance metrics for these 4 selected appliances, which are the clothes dryer machine, the dishwasher, the heat pump appliance, and the wall oven appliance. Our proposed method adapts a modular way to address dimensionality issues that arise as the number of appliances increase. Also, we use Bayesian optimization to tuning our hyperparameters. Finally, our model is a sequence-to-sequence regression model. This means that in our network, as input, we have not a single point values, but sequence data. And the output is the same, sequence data. The second proposed solution examines the possibility to use a CNN structure for energy disaggregation. In this work, we present a CNN-based approach for energy disaggregation, which is called multi-channel recurrent tap delay line CNN, which introduces three aspects to address challenges in NILM. First, since disaggregation of total consumption includes inherently recurrent elements, our approach endows CNN with a recurrent property that takes into consideration and past estimation outputs. Secondly, we adapt our proposed model to incorporate except of active power and some other components such as reactive power, apparent power, and current. Finally, we propose a 2CNN architecture to increase robustness to noise. In particular, the architecture employs a second CNN which utilizes the output of the first CNN along with the input of the previous CNN. Our model is a convolutional sequence-to-sequence NILM model. We form our data in a sequence chain-like structure to fit the CNN network. The time window of the aggregate signal covers a mean appliances duration. Output sequences are created with the same length as in the input sequences. This means that each time we feed the network with a whole sequence of appliance operation power load and not a single point value. So we propose a hybrid CNN model that incorporates RNN model characteristics into a basic CNN structure. The difference is that in the case of recurrent neural networks, models, the update occurs in the hidden state and not in the output. In our case, the update is carried out directly to the output. So we take the output from the first CNN as input to the second CNN model. So these are the three steps to create our final proposed multi-channel recurrent TDLCNN model. These diagrams show the loss progress for the training period between a basic TDLCNN form and a TDLCNN that has a recurrent character. We can see that the loss values during training are smaller for the second model. Until now, we have used only active power measurements as inputs to our CNN. Another tip is to use extra information and some additional features. In our example for MPDS dataset, we have include also reactive power measurement, apparent power measurement, and current. For each network, we have created a separate channel for each one of those components. So we have a multi-channel CNN architecture. The diagrams here are showing the loss function for the training period for these four appliances. We can see that the results for the multi-channel architecture are better. And here we can see the comparison between the multi-channel TDL-CNN architecture and the multi-channel architecture with a recurrent character. We can see that in most of the cases the loss error has the smaller values. So the figure shows the comparison among the predicted signal and the ground truth for the four appliances for our four created models. The final model is the proposed solution. We can see how robust it is to noise compared to the previous ones. A table shows the comparative results based on the objective metrics such as mean absolute error, root mean square error, and normalized root mean square error. The comparison is between our four models, a basic LSTM structure, a hybrid CNN LSTM structure, and the traditional combinatorial optimization and factorial hidden Markov models from NILM toolkit. So, to summarize, we use sequence-to-sequence regression models to gain knowledge from appliances' previous operation. Also, we use a CNN, two CNN. The first CNN focuses on the disaggregation part, and the second CNN focuses on the correction of the signal. And final, we use tensor inputs to enhance our model with additional information, not only for active power, and also for other components. These are our work. Thank you. And questions.